let's look at the function f of xy equal 9 minus x squared minus y squared. This is a downward opening paraboloid. I usually think of it as kind of like a mountain. So I'm going to draw it here. What I'm thinking about as I draw this is I'm thinking about drawing all the traces. So my trace in the YZ plane is just going to be 9 minus y squared. So it's going to look something like this. And my trace in the XZ plane is going to be 9 minus x squared. So it's going to also be downward open parabola. It's going to look kind of like this. And then in the xy plane, if I set z equal to 0, I'm going to get 9 minus x squared minus y squared equal to 0, or x squared plus y squared equal to 9, which is just a circle of radius 3. So there's my downward opening paraboloid. And what we're going to do is we're going to think about, imagine we are at the point 1, 2, 4. So we've got 1 in the x direction, 2 in the y direction, and 4 in the z direction. Like right about there. Oh, it's a little high. It's fine though. So we're on this level curve where z is equal to 4. So that right there, that's your point 1, 2, 4. Now what we're going to ask is, if you walk in the direction of the positive x-axis, so if I essentially, if I'm on this point and I'm walking towards you, am I going to go uphill or downhill? What kind of slope am I going to be traveling at? Well, if I walk straight towards you from this point, I'm not moving left or right. So y isn't changing. I'm just moving in the x direction, and then as a result of that, I'm either going up or down because I have to stay on the surface of this mountain. So if we look at what happens here, I'm going to draw, if I hold y equal to 2 constant, what's going to happen is I'm going to get this parabola like that, right there. And then to find the slope traveling towards you, I'm just going to find the slope of the tangent line in that direction. So the question we're asking really is, if we walk in the positive x direction, what slope will we have? Or in other words, what's the derivative in the x direction? So we're holding y constant. Specifically here, we have set y equal to 2. So if we actually just plug that in, f of x comma 2 is 9 minus x squared minus 4. And if we take the partial derivative here, and there's a couple ways of writing this. We can either write it as del f del x or fx. It's just going to be the regular if you can partial derivative. It's going to be negative 2x. And then if we plug in the point that we're at, which is 1, 2, 4, fx evaluated at 1, 2, 4, well, we can only plug in the x value of 1 and we get a negative 2 times 1, which is negative 2. What we're saying is at that point, if we move in the x direction, our slope is negative 2. Similarly, if we were moving in the y direction, well, we could take the same equation and find del f del y, or fy. You don't actually, so here you'll notice maybe that I plugged in y equal to 2 before I took the derivative. It's completely unnecessary. If I look at this function here and I say to myself, okay, x is acting like a constant now. We're holding x constant. And so whatever x happens to be, the derivative of x squared is going to be 0. So the derivative here with respect to y is going to be 0 minus 2y. And if we plug in the same point, our fy evaluated at 1, 2, 4 is going to be negative 2 times 2, which is negative 4. It's a little harder for me to draw because the picture starts to get a little bit complicated here. But essentially, we're saying that if instead of moving in the x direction that way, if we move in the y direction, which is left to right, we should have something that looks kind of like, sorry, it's always a challenge to get this to look right. Oh, it's okay. So there's the level curve when x equals 1, and we're finding the slope of that tangent line there, which is a steeper negative slope of negative 4. So that's the general idea of what a partial derivative actually kind of means. You're on this surface, and you've decided to ask what's the slope of the surface in this one particular direction. And for now, it's the positive x direction or the positive y direction. But eventually, very soon, we'll talk about finding the derivative in any direction. But we have to do this before we can do that. So let's look at some more examples. Not this, that, yeah, not. We'll get there in a minute, though. Holding one variable constant or imagining it is a constant is really kind of the whole story to finding partial derivatives. So just as a quick kind of reminder, if you have functions of one variable, if your function would say like tangent of x plus 3, the derivative would be derivative tangent is secant squared of x, and the derivative of 3 is 0. Or in other words, if you are just adding a constant on its own, its derivative is going to be 0. Whereas if your function was, say, 3 times tangent of x, that 3 doesn't go away. The derivative of a constant times a function. I like to say that the constant multiple just hangs out, and you take the derivative of the function to multiply by, which is going to be secant squared x. So constants on their own, their derivative is 0. Constant multiples get to hang out. So let's look at some examples. So let's say we have the following function of two variables. F of x comma y is equal to x to the 6th plus y to the 5th plus x squared y to the 3rd. And we want to find all the partial derivatives. When I say all, we're going to talk about the first and second partials. So let's find the first partial derivatives first. So I'm going to find fx, and it's really fine to write it either way. People go back and forth, just like we do with other regular derivatives, like y prime or dy dx or f prime or df dx. It's totally normal to write this as either fx or del f del x. Just as a point of notation, we don't really say f sub x. We really just do say fx. No one's gonna like get mad at me for saying it the wrong way, but just so that we all know what people are saying when what they mean when they say it. So here we're gonna get the derivative of x to the 6th is 6x to the 5th. The derivative of y to the 5th is 0, and the derivative of x squared times y cubed. While the y cubed is acting like a constant multiple, the derivative of x squared is going to be 2x, and we're still multiplying by the y cubed that's hanging out. And then you get rid of the 0 if you want to, and just write it as 6x to the 5th plus 2xy cubed. Similarly, the partial with respect to y, fy, del f del y, derivative of x to the 6th is 0, the derivative of y to the 5th is 5y to the 4th, and the derivative of x squared times y cubed, now the x squared is the constant that's hanging out, and the derivative of y cubed is 3y squared. And if I was going to write this in a more normal way, I write it as 5y to the 4th plus 3x squared y squared, just pulling that constant in front. So those are the first partials. Typically, we like finding the first partials and the second partials because those are the things we need to then find and classify the critical values of a function of two variables. So second partials, there's technically 4 of them, although someone might say there's only 3. So we're going to find fxx, which is just the derivative with respect to x of fx, which you could write that way. I just want to show you all the ways to write this because, again, we're going to go back and forth. You might also write this as del x of del f del x, which is then more compactly written as del squared f del x squared. Just the usual kind of second derivative notation, but with a del instead of a d. In case it's not clear what I mean when I write that, when I say del, it just looks like a curly d. And the reason we're using that is because when you have a function of two variables or more variables, we have to take partial derivatives, not just regular derivatives, because there's another variable that's kind of not in the mix. So here, I'm literally just taking the derivative with respect to x of my fx, which was 6x to the fifth plus 2xy cubed. And the derivative of that's going to be, the derivative of 6x to the fifth is 30x to the fourth. And the derivative of 2x times a constant is 2 times that same constant. So you get 30x to the fourth plus 2y cubed. Then sure, we'll do that. Yeah, let's talk about fxy. So here's where the notation gets a little bit wonky, I feel like. fxy means first you do the derivative with respect to x, then with respect to y. But in the other type of notation, it means this. It means the derivative with respect to y of the partial with respect to x. So, right, this notation also means x first, right? We did the derivative with respect to x, and then after that, y. And so you can also write this as del y of del f del y, which is really del squared f, and be careful. Oh, I made a mistake over there. It's del y of del f del x. Sorry about that. Which then we can write as del squared f del y del x. So be careful. Depending on which way you write the notation, it is going to appear out of order. This way, x first, y first means you do x first, then y first. This way, you read from right to left, and we do x first. Either way, we're going to end up getting the derivative with respect to y of our fx, which is going to be the derivative with respect to y of 6x to the fifth plus 2y cubed, which is going to be 0 plus the derivative of 2 times x times y cubed is 2 times x times 3y squared, which is going to be 6xy squared. Now, really, I wouldn't write all this if I was doing this, right? Like I would say, okay, I'm going to take the derivative with respect to y of my derivative with respect to x and just look over here and be like, okay, there's my fx, take the derivative of that with respect to y and get 0 plus 2x times 3y squared. Let's look at the other second partials as well. So we also have fyy, which we're not going to write all this stuff for. I'm just saying, I'm going to point out it's going to be del squared f del y squared. And so really I'm taking the partial with respect to y of my partial with respect to y, which was 5y to the fourth plus 3x squared y squared, which ends up being the derivative of that is 20y cubed. The derivative of that's going to be 3x squared times 2y, which is going to give us 20y cubed plus 6x squared y. And finally, the mixed partial fyx, which is del squared f del x del y, or the partial with respect to x of my partial with respect to y. Well, taking the derivative of this with respect to x, we're going to get exactly 0 plus 6x times y squared. And not coincidentally, the mixed partial one way ends up being the same as the mixed partial taken the other way. And that is generally true. In fact, let me go back and look here real quick. Just 1 sec. Just want to see one thing. Yeah. So typically, yeah. So what's happening here is this is something called Clairaut's theorem. Basically, the real truth is that in this class, they're always going to be the same. We're not going to encounter functions that are weird enough where the mixed partials are different depending on which way you do it. But generally, we say that if a function has continuous second partial derivatives, then the order in which we find the mixed partial. Doesn't matter. Or said more succinctly, if a function has continuous second partial derivatives, then it's going to be true that the mixed partial fxy is equal to the mixed partial fyx. Cool. So let's look at one more example. Yeah, because there's a few funky things. Yeah, let's look at that.
Is that ever not true?
So yes, there are functions where it is not true, but they are complicated. In fact, let me, there is a handout here. Let me grab it real quick because I think it's worth noting. I always forget what the function is exactly, but let me just grab it because I'm glad you asked. Let's see here. Yeah, one sec. There. So we'll look at this briefly, just because I do think it's worth addressing. Again, it's not something we need to worry about in this class because the examples like that don't usually come up. Sorry, 1 second. Where'd you go? Sorry, there is an example of this. I just need to find it. There we go. So here is one of the simplest functions I'm aware of where this doesn't work out. So the function is f of xy equal to x times y times the quotient x squared minus y squared over x squared plus y squared, as long as x and y both aren't 0. And then it's equal to 0 when x and y both are 0. So this function takes a bit of work, but if you do it, you can find that the partial with respect to x is equal to this monstrosity, x to the fourth y plus 4 x squared y cubed minus y to the fifth, all over x squared plus y squared using the quotient rule. And similarly, you can find fy is equal to x to the fifth minus 4x cubed y squared minus x y to the fourth over x squared plus y squared. And if you take the partial and plug in 0y here, you get negative y. So the partial first with respect to x is negative y. And then the partial of this, sorry, let me back that up. The partial of this evaluated at 0, y is negative y. The partial of this evaluated at x, 0 is positive x. But then if you take the derivative of that, you're going to get both 0 and 0, because if you plug in 0 for y, you're going to get 0. If you plug in 0 for x, you're going to get 0. So the partial derivatives are there. Sorry. And then if you do the partial derivatives using the limit definition, which is kind of a funky thing to do, but if you do it that way, you end up getting that the mixed partial fxy is negative 1 at the point 0, 0. And the mixed partial yx is positive 1 at point 0, 0. It's a little bit weird, but yeah, it's this very kind of strange thing where the mixed partial is not the same. But I just want to point out this weird, strange piecewise function is kind of the easiest example that we know of where the mixed partials don't end up being the same as each other at this one point. So I think all the functions we encounter in 16C are always going to have the mixed partials being equal to each other, because all the functions we encounter are typically not piecewise things like this. So I would say we don't really typically worry about it, but you're right. There are examples of functions where this is not always true. We just don't see a lot. So let's see, where were we here? I'm just going to look at some other interesting, some slightly more challenging examples of finding these partial derivatives, because the functions can get a little bit harder to deal with. Like, so this example, you might notice, didn't require anything other than the power rule, but there are certainly other derivative rules we should be aware of. So let's look at a more complicated example like the following. Let's say our function f of xy is equal to the natural log of x squared plus y plus e to the x cubed minus y squared. And now we want to find all the first and second partials of this function. So again, same idea, to be a little extra careful here. So let's start with the fx. And I'm writing both notations because I want to show them. I don't think you should as a student. Like, you should just pick one or the other, or use the one you're being given. So let's see. So del f del x, we're going to get the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the inside. Well, the derivative of the inside with respect to x is just 2x, right? Because the y, its derivative is 0. Plus, the derivative of e to the stuff is e to the stuff times the derivative of the stuff. But again, the derivative of x cubed minus y squared with respect to just x is 3x squared. Let's find fy. So same idea. We're using the chain rule for both of these. The derivative of the natural log of this stuff, again, is 1 over the stuff. But now instead of multiplying by 2x, we're multiplying by the derivative with respect to y, which is just 1. Which I probably wouldn't write, but you know. Plus, the derivative of e to the stuff is going to be e to the stuff times the derivative of the stuff. But now it's the derivative of x minus y squared with respect to y, which is going to be negative 2y. I will point out, kind of after the fact, but that's all right, that we could have written e to the x cubed minus y squared as e to the x cubed times e to the minus y squared, and then just kind of viewed it as a function of x and a function of y. So if we differentiate with respect to x, we're going to get, like, for example, the partial with respect to x here would be e to the x cubed times 3x squared, and then this other part just hangs out, which is exactly the same as what we've written here, just written slightly different. I shouldn't say fx, I should say the partial with respect to x, whatever. But now when we start finding the second partials, it's going to be a bit more complicated because, well, I'm going to rewrite these just slightly. I'm going to think of this as 2x over x squared plus y. And this is, I'm going to have to use the product and the quotient rule. So it's going to get a little bit messy here. So let's find fxx. I don't really want to write down the derivative of the derivative. I'm just going to look at this first derivative and start taking its derivative. So I see a quotient 2x over x squared plus y. That's going to be the bottom times the derivative of the top, which is 2, minus the top times the derivative of the bottom, which is 2x, all divided by the bottom squared. And then for this part here, the e to the x cubed minus y squared times 3x squared, I'm going to have to use the product rule. So it's going to be the derivative of the first part. So the derivative of e to the x cubed minus y squared is again e to the x cubed minus y squared times 3x squared. And that's going to be multiplied by 3x squared. Plus, when we switch it up, we leave the e to the x cubed minus y squared alone. And we multiply by the derivative of 3x squared, which is 6x. A little bit messy, but it helps, right? You can think of this as your u, that's your v, there's your u prime times v times v prime. And so you could also do that here, right? You could think of this as like, I'm not using f and g because I've already used f's, but you could think of this as like your u over v, and then the derivative is the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. If it helps to write those things, but not necessary. Let's look at, so the order I typically do these in is fxx, then fyy, then the mixed partials. I don't know why I do it that way. I'm going to find fyy next. Probably the reason really is because when there's a thing we calculate later on called the discriminant, the determinant of the Hessian, and it's fxx times fyy minus fxy, that part squared. So that's probably why I do these two first. So fyy, not quite as terrible. In fact, for fyy, instead of using the quotient rule here, I might actually think of the 1 over x squared plus y squared just as x squared plus y squared to the negative 1. So taking the derivative of that with respect to y, we're going to get negative 1 times x squared plus y squared to the negative 2 times the derivative of the inside, which is 2y. Seems a little bit less terrible than the quotient rule. And then over here, we're still going to have to use the product rule. So again, derivative of this is going to be e to the x cubed minus y squared times negative 2y and then times the other negative 2y that was already sitting there, plus then it's the e to the x cubed minus y squared on its own, times the derivative of negative 2y, which is negative 2. Right, let's do the mixed partials. So now we're going to do fxy, which, yeah, I'm going to write as the derivative with respect to y of fx. Again, I don't think you really need to write this, but it kind of helps. So I'm looking at fx, and I'm taking, ooh, I made a small mistake here. It's not a huge mistake, but it is a mistake. Somehow I saw this as x squared plus y squared, not x squared plus y as it was originally written. So let's be a little bit careful here, James. I should really, so here's the, ooh, yeah, that's going to change things up. So let me actually fix this. Sorry about that. So what I should really have here, yeah, good job. I should really have had negative x squared plus y to the negative second times the derivative of y is just 1. And then the rest of this should still be the same. So I probably didn't need to rewrite all of it, but I started and now I can't stop. Sorry about that. Okay, now let's look at those mixed partials. So might as well make our lives easy here and say that we want to find fxy, which is again the derivative with respect to y of your fx. I'm just looking at my fx and then I'll take the derivative with respect to y. Again, it might actually, yeah, I am going to do one more thing here. I'm going to write this out. I'm going to write out fx in the way that's going to make my life easier. I'm going to write it as 2x times x squared plus y to the negative first, plus this part over here, which is just 3x squared times e to the x cubed minus y squared. And again, we're differentiating with respect to y. So as far as we're concerned, this 2x is just hanging out. It's a constant multiple. The derivative of some stuff to the negative first is negative 1 times our stuff, the negative second times the derivative of the inside, which is just 1. Yeah, that's fine. Plus the derivative of all this, well, again, the 3x squared is just a constant as far as y is concerned. And the derivative of e to the stuff is e to the stuff times the derivative of that stuff, which is going to be a negative 2y. It's always a good exercise to see that if we do it the other way, we do in fact get the same result. So let's go ahead and find the mixed partial the other way. So fxy, I wrote the same thing. Not fxy, fyx, which is going to be del x of fy. And I am going to do the same kind of thing. I'm going to rewrite this just to make it a little bit easier. That's going to be del x of x squared plus y to the negative first, plus negative 2y times e to the x cubed minus y squared. I wouldn't normally put the parentheses on the minus sign like that, but I'm going to have to use the product. No, actually, I'm not. I could have just dropped the parentheses, but well, I didn't. So now taking the derivative of all this with respect to x, we're going to get derivative that's going to be negative 1 times our stuff, the negative second times the derivative of the insides with respect to x. So that's a 2x plus our negative 2y hangs out, and the derivative of e to the stuff is e to the stuff times the derivative of the stuff, which is just 3x squared. And if you compare this with this, they should be the same. Let's see, up here, I have a 2x times a negative 1 times an x squared plus y to the negative 2. And down here, I have a 2x times a negative 1 times an x squared plus y to the negative 2. And over here, I have a 3x squared times e to the stuff times negative 2y. And over here, I have a 3x squared times e to the stuff times negative 2y. So yeah, they're the same. And they should be the same. Let's take a look. One second.
If we like accidentally write D instead of del, that'll actually.
No one's looking. But so just for your knowledge, right? The del is curly or the D is like a straight line. And then you're supposed to write del. So the problem is a lot of times when we do some of this stuff, when it gets more complicated, talking about a different version of the chain rule, you have del's and d's. Because if you have a function of just one variable, its derivative is d whatever. But if your function is a function of more than one variable, then you're supposed to write del. But yeah, you're right. No one's looking. And if you're really slick, you just kind of write, you can write like a halfway between like something that's vaguely curly, but could be straight enough if it needs to be here or del, but no one's looking. Yeah. So let's look at and we can also have functions of more than two variables. So for example, if we had something like maybe f of x comma y comma z equal to x squared times sine of 2y plus z cubed, then we could find all the first partials. So certainly our fx would be 2x times that constant. It really does pay to get used to just saying whatever variables I'm not differentiating with respect to, they're going to be a constant. So once I saw that there wasn't an x over there, I'm like, great, that's a constant, at least for the moment. Now for fy, x squared is a constant, but sine of all that's not a constant because there's a variable in there. So now I have to treat this like a function. The derivative of sine of some stuff is cosine of the stuff. And the inside stuff doesn't change, even though there's a z in there, right? That stuff has to stay as is. But then we multiply by the derivative of the inside, which is the derivative of 2y, which is 2. Because the z cubed is a constant. And similarly, fz, or if you want to write del f del z, if you like that notation, is going to be the same sort of thing. The x squared still hangs out as a constant. The derivative of sine of some stuff is going to be cosine of the inside stuff. And then we multiply by the derivative of the inside, but now the derivative with respect to z, so we're going to get a 3z squared. And then you could ask all sorts of like kind of what so you can do mixed partials kind of any way you want, but you could also go more. Like someone could ask you to find, for example, what's like f x z x, meaning first x, then z, then x, which you could write kind of terribly as del cubed f over del x del z del x. And so then you would first do fx, which we've already done. And then you would do the derivative of that with respect to z. So fxz, which is x first, z second, would be 2x times cosine of 2y plus z cubed times 3z squared. And then you take the derivative of that with respect to x again, and fxzx would be 2 times all that. So you can ask kind of any combination of mixed partial you want. Yeah. Yeah, we might as well. So the place we're kind of going with this is that the idea here is we're going to use these mixed partial derivatives to find critical values of our function of two variables in a way very similar to how we found critical values of one variable, functions of one variable in 16a. Where we're going to take a derivative and set it equal to 0. But now it's a little bit more complicated. Let's look at some examples that are not terrible here. 1 second. Yeah, that's fine. So let's say we had something like this. Yeah, we'll do that. So let's look at this function here. Let's look at f of xy equal to x squared plus y squared minus 4x plus 6y is 9. And I want to find the critical values. So actually I should really call them critical points. To find the critical points of this function of two variables, we're going to set both partial derivatives equal to 0. Because here's what we're really looking for. So this shape, I'll just tell you, this is an upward opening parabola. It looks kind of like this. And we're essentially trying to find where you might have a minimum or a maximum, which certainly looks like it's probably the bottom right there. And what's special about this minimum or maximum is its tangent plane is parallel to the xy plane. Right? If I draw the tangent plane here, right, it just looks like I'm touching that plane that's essentially sitting flat, meaning the derivative in any direction is going to be zero. Right? If your plane is horizontal, you're not going up or down as you move along it. So we're thinking, oh yeah, both the derivative in the y direction and the derivative in the x direction have to be zero. So that's how we're going to identify, just like a function of one variable might look like this, and you're looking for the points where, oh yeah, the derivative is zero. So to find these critical points, we're going to set each of the partial derivatives equal to zero. So we're going to find fx. It's going to be 2x minus 4. We're going to find fy. It's going to be 2y plus 6. And we're going to set each of those equal to 0. And in this case, we're only going to get one solution. From this first equation, we're going to end up getting x equal to 2. From the second equation, we're going to end up getting y equal to -3. And so our one critical point is the point 2, -3. So then the question is, what kind of thing is it? Just like in 16a, when we found a critical point, it was either a maximum or a minimum, or neither. Right? Neither was also an option. Here we actually kind of have the same three options. So either your critical point is going to be a maximum, or it's going to be a minimum, or it's going to be kind of a neither thing, which is like a saddle point, which is a maximum in one direction and a minimum in another direction. And how do we do this? Well, to classify this, we calculate the determinant of the Hessian matrix, which you don't actually have to know. We calculate this thing d, which is just the second partial with respect to x times the second partial with respect to y minus the mixed partial squared. And the mixed partial can be calculated either way. So let's calculate d. D is going to equal fxx, which is 2, times fyy, which is also 2, minus fxy, which happens to be 0 here, squared. So d is 4. So when d is positive, one of two things can be true. You can either have a maximum or a minimum. It's going to be a maximum if, so here's what I can think about it. It's going to be a maximum if the function is concave down. And the function is concave down if its second derivative is negative. So it's a maximum if every week, every day it feels like that's just like, sorry, that's like, I'm just ready for it now. So a maximum if it's concave down. And I really encourage you to think of it that way, because I can remember, I encourage myself to think of it that way, because I remember that a function is concave down when its second derivative is negative. So concave down, aka either second derivative is negative. Similarly, it's going to be a minimum if it's concave up, meaning either second derivative is positive. And that's what we have in this case, right? Here are both our second derivatives. There's your fxx, there's your fyy. Since d is positive and fxx and fyy are both positive, then it's going to be concave up, which means we have a minimum. So we have a minimum at 2, -3. Which we were expecting, because we already kind of said we knew that the graph was going to be an upward opening parabola, so it would make sense it's going to be a minimum. In fact, just to show a little bit more here, if you wanted, we could actually complete the square here and say this is x squared minus 4x plus 4. plus y squared plus 6y plus 9. And then adding a 4 and a 9, so I just need to subtract the 4 and the 9, and then there's still that plus 9 there. So really, we could rewrite this as x minus 2 squared plus y plus 3 squared minus 4. And then you can really justify to yourself that, oh yeah, if x is 2 and y is negative 3, that's the smallest that can ever be. So it's certainly a minimum. We don't need to do that, but it's nice to be, oh yeah, it works the way we think it should. Let's look at another example here, because
So that's just, like on tests and stuff. Would you be required to calculate to determine if it's like minimum maximum, or would you be able to just like graph it?
typically, so the thing is, many of them are too complicated to graph. So let's look at an example where we actually have that going, because I do think it's worth pointing out here. But yeah, there are some things that you can graph. In fact, and there are some functions where you can't find this. So let me say two things. Thing one, let's first talk about what D needs to be. So to classify critical points, we calculate D evaluated at them. So I'll point out the last one, there wasn't anywhere to plug in x being 2 and y being negative 3, but in other examples, there will be variables left after we've differentiated where we then plug in to see what we've got. But first we calculate D, which is fxx and fyy minus fxy squared. And then you have essentially three options. One, if D is negative, then we have a saddle. If D is positive, then you have to do more work. Then you either have a maximum if we're concave down, which is just another way of saying that fxx is negative, or you have a minimum if you're concave up, which is another way of saying fxx. It doesn't actually matter, you can say either one. Fxx is positive. I'll point out that if D is positive, fxx and fyy have to have the same sign. Because if they didn't, then that would be negative, and the negative number minus something squared would be even more negative. So if D is positive, fxx and fyy are either both positive or both negative, which is why we only talk about fxx here. You could just as easily talk about fyy. You're always guaranteed that they'll be the same sign. And then lastly, if D is 0, then it's inconclusive. A very kind of typical example of this is, for example, the function f of xy equal to x to the fourth plus y to the fourth. If you take the partial derivatives and set them equal to 0, you'll get a critical point of 0, 0. And then if you take the second partials, you'll get like 12x squared and 12y squared. And so your D would be 12x squared times 12y squared minus the mixed partial is 0. And then if you plug in 0, 0, what do you get? Get 0. So D of 0, 0 is 0. So the test is inconclusive. However, it's fairly easy to justify to ourselves, kind of like in the previous problem, that if you plug in 0, 0, you for sure have a minimum because that function is always non-negative. So sometimes when it's inconclusive, there are other ways to go about figuring out what's happening. So let's look at one example before we run out of time here. Let's see here. Yeah, I like that one. That's a good one. So let's say we have the function f of x comma y equal to 6x squared plus 6y squared minus 3x squared y minus y cubed. Which I'll point out, I have no idea how to graph. Like, other than typing it into Desmos and seeing what it looks like. It might look really neat. That's not the point. So we're going to find the critical points by setting each of the partials equal to 0. So fx is going to be 12x plus 0 minus 6xy. So that equal to 0. And fy is going to be, let's see, 12y minus 3x squared minus 3y squared equal to 0. Both of these look not great. if I have an option, I'm always going to try and deal with the simpler one, for lack of a better phrase. And I would say the first equation looks simpler to me because I can factor out a 6x and write it as 6x times 2 minus y equal to 0. So there's two potential solutions to this first equation. Either x equals 0 or y equals 2. I cannot stress enough, 0, 2 is not a critical point. Because to be a critical point, you have to satisfy both of these equations equaling 0 at the same time. You plug in 0, 2 here, sure, great. If you plug in the 0 for x and 2 for y down here, you're going to get 24 minus 0 minus 12, which is not 0. So what we do with this information is we take each one of these as kind of their own thing. So if I plug in x equal to 0 to this equation, then I'm going to have 12y minus 0 minus 3y squared equal to 0. Factor out of 3y, and you're left with 4 minus y. So when x is 0, there were two possibilities for y. You either get y equal to 0 or y equal to 4. So I've already got two critical points. I've got 0, 0 and 0, 4. And then if I plug in y equal to 2 into this equation, I'm going to have 24 minus 3x squared minus 3 times 4 is 12 equal to 0. So 12 minus 3x squared equals 0. Factor out of 3 out of 4. And you're left with 4 minus x squared equal to 0. So the solutions are x equal to plus or minus 2. So my two other critical points here are 2, 2 and negative 2, 2. And then we find our d. So d is going to equal, let's see, fxx is going to be 12 minus 6y. fyy is going to be 12 minus 6y. And fxy is going to be, like in the first one, 0 minus 6x. So negative 6x squared. So there's our d. I would almost never recommend simplifying this because you don't really care what it looks like on its own. You really just care what happens when you start plugging in points. So if I plug in the critical point 0, 0, look what happens. I get 12 minus 0 times 12 minus 0 minus 0 squared. That's going to be greater than 0. I don't actually care that it's equal to 144. And then since it's positive, we know we either have a maximum or a min. But then there's your, this is also why I don't simplify it. Because then you can just see, oh, look, there's your fxx. And since fxx is positive, we know we have concave up, which means we have a min. So fxx is positive, concave up, we have a minimum at 0, 0. And then you can do the same thing for the other three critical points. So if you plug in 0, 4 is not, let's plug in 2, 2, just to kind of see what happens. So you plug in 2, 2, you're going to get 12 minus 12, which is 0, times 12 minus 12, which is 0. It doesn't really matter, it's 0. Minus negative 12 squared, which is certainly going to be negative. So at 2, 2, we have a saddle. At 2 o'clock, I'll stop talking. But I will say, you're also going to get a saddle at negative 2, 2. And you are going to get a maximum at 0,